So problem 6.4 is to study the continuity of these functions. Okay, there are 14 of them, and so let's start with the first one. Okay, first, f of x is e to the minus 5 of x plus the cosine of x divided by x squared minus 8x plus 12. Okay, so now this f is the fraction between these two functions, right? Let's call them g, e to the minus 5 plus cos, and h is x squared minus 8x plus 12, right? Now these two are continuous functions, right? This is the sum of two continuous functions. The exponential is continuous, the cosine is continuous, and then 8 is a polynomial, so it's continuous, right? So f will be continuous except in the points where the denominator h is 0, okay? And h is 0 in where x is 2 and x is 6, okay? You can compute it on your own, right? So then this is continuous in r minus these 2 points, right? Okay, that's where the first one is continuous. Okay, and the same approach we will be doing for every other function, right? Now f in part 2 is e to the 3 over x plus x cubed minus n. Now f is the sum of three functions. X cubed is continuous, 9 is continuous. Now what happens with e? E is this is g, okay, which is the composition of the exponential and 3 over x. Now the exponential is continuous, so now the only point of this continuity is where 3 over x is discontinuous, which is at 0. Okay, so this is continuous in r minus 0, okay, except 0. Okay, and you can compute the limit, the one-sided limits of this g exponential of to 3 over x when you go to x to 0 from the left and from the right, and you will see that there's a discontinuity there. Okay. Okay, let's do 3. F of x is x cubed times the tangent of 3x plus 2, right? X cubed is continuous, and the tangent is discontinuous at the, so tangent is discontinuous, tangent of x, right, at the odd multiples of pi over 2, right? So 2k plus 1 over 2 pi, right, where k is a real natural number. Well, it's actually an integer number, okay, every integer number. So you have the tangent here. This is what it does, right? We know that this does something like this, but it does something like this again. This is 3 pi over 2, so pi over 2, 3 pi over 2, minus pi over 2, and on and on, right? It's a periodic function. It repeats itself after every pi, every interval of length pi, right? So the discontinuities of the tangent are at when x equals 2k plus 1 times pi over 2. Now this f will be discontinuous where 3x plus 2 equals 2k plus 1 over 2 times pi, right? If we solve for x, we have that x has to be equal to 2k plus 1 pi minus 4 over 6. Okay, that's where f is discontinuous at these points. Okay. Okay, let's do part 4. Part 4 is f of x is the square root of x squared minus 5x plus 6. Now this is the composition of two functions, right? The square root of x and this parabola, right? X squared minus 5x plus 6, right? So f of x is g of h of x, right? Decomposed with h. But now we know that both g and h are continuous functions, right? The square root is a continuous function, the polynomials are continuous. So f is the composition of two continuous functions. F is going to be continuous in its domain, right? And the thing is that the domain of this function is not R, right? It's only, the domain is only where this thing is greater than 0, okay? But in its domain it is continuous, okay? And the domain, you can compute the domain of this function is minus infinity to 3 infinity, okay? This is the domain. So it's continuous here, okay? To part 5. 5 is f of x is the arc sine of x cube, right? So again, this is the two functions, x cube and the arc sine of x. So f is what g composed with h, okay? But both g and h are continuous in their domain, and so f will be continuous, okay? Now the domain of this function is the domain of the arc sine, which is minus 1. The domain is minus 1, 1, okay? So in this domain it will be continuous. Okay, let's do 6. F of x is x minus 5 times the logarithm of 8x minus 3. Now again, f is the product of two functions. This is a polynomial, it's continuous, the logarithm is continuous, f is continuous in its domain, okay? The domain is wherever the logarithm is defined, so that means 8x minus 3 has to be greater than 0, so x has to be greater than 3/8, so d is 3/8 infinity, right? Okay, let's do 7. Part 7 is f of x is x minus the integer part of x. Okay, that's an interesting one, right? So we know that the integer part of x is this step function, okay? That's the greatest integer that's smaller than the number, right? So whenever you have a positive number, it's 0. If x is between 0 and 1, it's 1. If x is between 1 and 2, it's 2, right? 1, 2, right? If x is between 2 and 3, so it goes on, and it's minus 1 if x is between minus 1 and 0. It's minus 2 if x is between minus 1 and minus 2, and so on, right? Now, if you think about subtracting x minus its integer part, right? If you think about positive numbers, right? So x is whatever point, okay? So x can be 5.16, what, I don't, okay? Now, the integer part of x is going to be 5, right? So x minus the integer part is always going to be some number in 0, 1, okay? And so that means that, you know, for points between 0 and 1, you have the absolute value, sorry, the integer value of x is 0, right? So x is, you have this, right? And when you get to 1, right, what you have is that the integer part becomes 1, so it's 1 minus 1, it becomes 0, right? But then it's still, this function does not change the integer part, okay? This is the integer part of x, and this is x minus the integer part. So the integer part that doesn't change, but x keeps growing, so it still grows like this. And when you get to 2, right, then it's 2 minus 2 again, so it goes back to 0. Okay, so you can easily see that this function is going to be like this, right? It's going to grow. It's like a ladder that goes up and then falls down, right? So the points of this continuity are where x is an integer number, right? So it's discontinuous in z, okay, the set of integer numbers. Okay, now let's go for 8. 8 is a function that's defined piecewise, right? So x squared sine of 1 over x when x is different than 0, and 0 where x is 0, right? Right, so whenever we have piecewise functions, right, we have, well, first we study the continuity of the two or the pieces that we have, right? In this case we have x squared times the sine of 1 over x. So this is a continuous function, and this is a continuous function except the 0, which is the point where there could be a discontinuity. So if x is different than 0, this part is going to be continuous. 0 should be continuous, but it's only defined at a point, so we can't talk about the continuity here, right? So in order to see if the function is continuous at this point is to see if the limit when x goes to 0 of f of x exists, okay, and it's 0. Okay, do you see? So we have this function for every value of x that's different than 0. So the limit when we approach x from the left and from the right of this function, it should be 0. Okay, so if the limit exists and it's 0, then the function is continuous. Okay, but the limit when x goes to 0 of x squared sine of 1 over x is 0, as we have seen, because this is, we can use the sandwich theorem, right? This is bounded by 1 and this goes to 0, so that's okay. Okay, so this function is continuous in R. Okay, let's do part 9. 9, another piecewise function. F of x is the tangent of x divided by the square root of x wherever x is greater than 0, right? Now 0 if x is equal to 0, and e to the 1 over x if x is smaller than 0, right? Now for every part we have to study the discontinuity of those functions. We know here we have the square root of x in the denominator, but x is greater than 0, so this is okay. But the tangent of x is discontinuous in, we have seen 2k plus 1 over 2 times pi, where k is a natural number. Okay? Well, we can talk about, we can say 2k minus 1, and then that includes 2k, sorry. This is 2k minus 1. So when k is 1, this is pi halves. So this is the first discontinuity, okay? So first part is this, right? This is discontinuous in these points, okay? In all these points. Now, when x is negative, this is c to the 1 over x. If x is negative, this is going to be continuous, so that's fine. And then we have what the problem at 0, okay? So we need to find first that the limit when x goes to 0 from the right of f of x is equal to the limit when x goes to 0 from the left of f, and it has to be equal to 0, which is the value of the function at 0, right? What's the limit when x goes to 0 from the right of f? Well, if you go from the right, you have to take this part of the function, so this is a tangent of x divided by the square root of x. Now, the tangent of x, we know it's asymptotically equivalent to x, right? So this is the same as this fraction. This is the limit of the square root of x when x goes to 0. This is 0. Okay. And then the limit when x goes to 0 from the left is the limit of this, e to the 1 over x, which is exactly equal to e to the limit when x goes to 0 from the left of 1 over x. This is, we know, minus infinity, e to the minus infinity is 0. So the function is continuous at 0, okay, but also discontinuous at these points, 2k, odd multiples of pi halves, okay, which are the discontinuities of the tangent. Okay, so let's go to part 10. Part 10. Now f of x is x if x is a rational number minus x if x is not a rational number. Okay. So let's see. If we're getting to this means that the limit when x goes to any point a of f of x has to be a, right? But the limit whenever we get to every point a, it doesn't matter if it's rational or irrational, the limit doesn't exist, right? Because sorry, the limit of this is f of a, sorry. Okay, this limit doesn't exist for every number, every positive or negative number, because even if it's rational, the limit, you know, every close to or in an environment of x there are an infinite number of irrational numbers and rational numbers, so the function is not going to converge. And also for a negative number, right? Now the thing is, when you get the limit when x goes to 0 of f of x, that is going to be 0, okay? Because you're getting closer and closer to 0, so it doesn't matter that this sequence, if you think about any sequence that goes to 0, it's going to be alternating, maybe if you go to irrational or rational numbers, but all of them are going to approach 0 as the sequence, the n goes to infinity. So in this case, the limit of f of x is which is f at 0, right? So 0 is a rational number, this is 0, okay? So that's the only case in which this function is continuous, okay? So this function is discontinuous everywhere except at 0. Okay? Okay, let's do part 11. So f of x is the sine of pi x if x is smaller than -1. Now the absolute value of x minus x if x is between -1 and 1, and then x minus 1 cubed if x is greater than 1. Okay? Now each of these three functions are continuous on their own, right? Or not. Let me see. So this is the sine of pi x. It's a continuous function. This is a polynomial. It's a continuous function. And then the absolute value of x minus x. The absolute value is a continuous function minus a continuous function is going to be a continuous function, right? So the three of them are continuous. So the only problem now is to see. So this is continuous everywhere except in the points where these pieces are connected, right? So we need to compute to check that the limit when x goes to -1 of f of x exists, okay? And so and the limit when f of exists, sorry, and coincides, and it's f of -1, right? And the limit of when x goes to 1 of f of x exists, and it's f of 1, right? So we know that let's start with f of -1 is this, and then we have the absolute value of -1 is 1 minus -1 is 2, right? If I'm correct. Oh, wait a minute. Yes, it's 2, right? and then the limit when x goes to -1 on the left, from the left, right, is the limit of the sine of pi x, and the limit of sine of pi x, this is identically 0, right? It doesn't matter what value x takes. Well, not sorry, it's not identically 0, sorry, but when the limit of this is just when x is -1, but when the sine of minus pi is 0. Okay, and this is the limit when x goes to -y on the right, right? Because this function is continuous, so when you calculate this limit, this is the interval in which this definition, this function is f, so this applies, right? Okay, so the function is discontinuous at -1, okay? Because the limit from the right is so from the left is different than the limit from the right, okay? 0 is different than 2. Now, can we do this for 1? Okay, so what's f? The limit when x goes to 1 from the right of f of x is going to be f of 1, right? Again, and sorry, there's a problem here. It's not more equal, it's just smaller. Okay, so when you approach 1 from the right, the limit of this is going to be f of 1, in this case 1 minus 1 cubed, which is 0, right? Because that's where the function is defined at 1 is here, right? Now what's the limit when x goes to 1 from the left of f of x? Is the limit of this, the absolute value of x minus x, then we do the substitution, it's 1 minus 1, which is 0. Okay, so this is equal, that means that the function is continuous at 0, sorry, at 1, but discontinuous at -1. Okay, okay, now you can try and plot in these functions some software so that you can see how this works, right? Okay, f of x is x plus 1 squared the sine of x plus 1, so this is when x is smaller than 1 minus 1, when the sine of x when x is between 1 and -1, and then 2x whenever x is greater than 1, right? Now what's the sine of x? The sine of x is a function that's -1 if x is negative and 1 if x is positive. Okay, that's what the sine means. So this function is continuous, this function is continuous. There's a discontinuity here at 0 because of the sine. Okay, so f is going to be discontinuous at 0 automatically. Okay, and then we need to check if everything connects, right? Just like before, the limit when x goes to -y from the left of x plus 1 squared is 0. The limit when x goes to -1 from the right of the sine of x plus 1 is when you go to -1 from the right, the sine of x is going to be negative, so this is -1 plus 1, this is also 0, so the function is continuous at -1, and then we compute the limit when x is going to 1 from the left, so this is the sine of x plus 1, which is 2, right? The sine of x is positive, and then the limit when you go to 1 from the right of 2x is also 2, so this function is continuous at 2. So the only point of discontinuity is at 0. Okay, everywhere else this function is continuous. Okay, then we have 13, right? Is f of x is x squared, the absolute value of x squared minus 1, 4x minus 5, and then the intervals between -2 and 2, and x is greater than 2, right? Now again, all of these, the three functions here are continuous, right? X squared is continuous, this is continuous, we know this is a composition of two continuous functions, this is also continuous. So we need to check what are the limits are at the discontinuities, right? The limits when x goes to -2 on the left of x squared is 4. The limit when x goes to -2 on the right is the absolute value of x squared minus 1. The limit of that, right? And so this is 4 minus 1, 3. Okay, so it's discontinuous at -2. And then we have the limit when x goes to 2 from the left is the absolute value of x squared minus 1. It's again 3. And the limit when x goes to 2 from the right of 4x minus 5 is 4 times 3 is 12 minus 5 is 2, right? Unless I'm doing something wrong. No. Wait a minute. 4 times 2 is 8, sorry. Minus 5 is 3. Okay, so the function is continuous at 2. Okay, so the only point of this continuity, again, it's -2. Everywhere else, the function is continuous. And then finally, we have f of x is x minus 1 squared whenever x is greater than 1, x minus the integral part of x whenever x is between -1 and 1, and x plus 1 whenever x is smaller than -1. Okay? Now, these x minus 1 squared and x plus 1 are continuous functions. X minus the integer part of x we've seen in 7, that it's discontinuous at the integers, so it's going to be discontinuous at 0, okay, automatically, and then we have to see what happens at -1 and 1. So again, what's the limit when x goes to -1 from the left is the limit of x plus 1, and this is 0. The limit when x goes to -1 from the right is the limit when x minus the integer part of x goes to -1 from the right. So that means 0 is x is between -1 and 0, so that means that this is -1, and then this is also -1, so -1 minus -1, it's also 0. Okay, and then the limit when x goes to, so this is continuous at x equals -1. The limit when x goes to 1 on the left is the limit when x minus the integral part of x, and if you remember the plot, this is going to be 1. The limit when x goes to 1 from the right is x minus 1 squared, the limit of this, but the limit of this is 0. Okay, so this is discontinuous at 1. So this function is discontinuous at 2 points, x equals 0 at x equals 1, and it's continuous everywhere else.